Great. All right. Well, welcome everybody. I want to welcome our speaker today, Wayne Sharfin, who is going to talk to us about something that I consider to be really, really important. You know, we live in a technology intense world, and I think it's important for the public at large to have an appreciation of how technology impacts their lives. And that is particularly true of teachers and of their students. The students will, in fact, be the folks who move our technology forward into the future. And so I think it's awfully important that we take into consideration how to best engage and excite young people about technology and its social implications. Today, we're going to hear from one of our members. Wayne has joined us on a number of occasions in the past. He's going to speak today about a science demonstration program to inspire undergraduates, underprivileged middle school students. Wayne has his PhD in laser spectroscopy from the University of Chicago. He focused his work on optical devices and worked for a number of years at GTE and also at MIT Lincoln Labs. He has served as a vice president for engineering for 3 different startup companies in the US and in Canada. And Wayne, we're delighted to have you. I really think what you're going to talk about today is extraordinarily important in going forward as a technology intense world. And I'm just delighted that you're taking an initiative to put together a program of the kind that you're going to describe to us today. So welcome. You can, if you would now like to screen share your presentation, we can begin, but floor is yours.
I'm going to start off by just verbally telling you what, why, and how I'm trying to do this, and then I'll put up the presentation.
Very good.
And by the way, it sounds like I can learn a lot from this crowd. I started this on my own. It's different. Don Nelson seems like he has a lot of experience teaching kids, but it sounds like he's mostly been teaching high school kids. The challenge in this is that I tried to get them in middle school because I figured that if they would be interested in science or technology, they would already want to know that in high school, where they would take preparatory courses like AP Calculus, physics, and things that are voluntary, which they might not take if they were not interested in science or engineering. So it's good to catch them in middle school. Now, one of the issues is that in recent years, we had the pandemic. So when you're talking about disadvantaged kids, and in addition, they're been handicapped by the pandemic, I tried talking to a lot of middle school teachers. It sounds like I could not even assume that they've taken any algebra. So that's a challenge. So in presenting science, I have to present it without a single equation. And so what I'm trying to do is set up in-school participatory, where possible, demonstrations to inspire interest in science and engineering from middle school kids. And I've gathered together a number of props to do these demonstrations. They're pretty simple because I didn't have a budget yet. And I will tell you what they are as I describe the demonstrations. So why am I doing this? Well, there's many after-school STEM nonprofit programs, but those are really for motivated kids. They already know that they're interested in STEM subjects. There's also some special STEM academies. I'll get back to that later, which they're public schools, so they are rated as public schools, which is interesting to see because the ones that I've looked at all have done very poorly in science and math standardized testing, yet they claim to be STEM academies. So I would assume that these students already have encouragement from supportive parents if they're going to these after-school programs. But I was hoping to reach students who might be disadvantaged by a home environment or family attitudes that could handicap them. Some examples might be a single-parent household with several siblings in a small apartment, television blaring. It's hard to do your homework. It's hard to do well in school, or someone who comes from an immigrant who comes from a different culture, which doesn't encourage girls from pursuing a technical education. Those are some of the people who I'm trying to inspire. If they're excited about science or engineering, then I'd like to offer them some kind of support outside their families that might see an opportunity to succeed. So, I think that, when they rate schools, they tell you that, for example, I live in Lexington. They say that Lexington has an excellent school system. I think if they looked at the variables that correlate with this excellent school system, the strongest correlation would be the average educational level of the parents, which these poor kids don't generally have. I mean, in Lexington, your mean free path before colliding with a PhD is about 100 feet. And there's professors from some of the world's best universities in the town. You could be sure that they want their kids to do well in school. That's not the case for these kids who come from these poor backgrounds. I also, when my father, who was an artist and a musician, and that's what my parents thought I was going to do, because I had won awards actually in both of those areas. I ended up going into science, but my father, I asked him why he didn't do art, and he said, well, because he couldn't make a living. So he was an art teacher as well, and he exchanged places with a teacher in England one year when I was in 4th grade, and we lived in a part of England which was the industrial Northeast, which is all coal and steel mining, coal mining and steel. We lived in West Hartlepool, and all the kids there went to the steel mills just like their fathers. They really didn't have a chance. They segregated them in the 6th grade to decide whether they would go to vocational school or to go to university. So how have I been trying to do this? Well, one limitation of the approach that I'm trying to take is that it requires support and cooperation from the school principal and the teachers, because I'm saying I want to come into the classroom and do demonstrations for the classroom. So I first tried to offer these demonstrations to schools in Lawrence, because that's a city where I had worked in my first year of a startup company when I was at Aegis Lightwave. We had about 10 people, and we had a single room in Lawrence, downtown Lawrence, and I actually had a fondness for the city. And so I tried to contact, after a lot of effort, I found, I was there about 25 years ago, but after a lot of effort, I found an enthusiastic assistant principal who thought this program would be great. He gave me a tour of the middle school in August. And then unfortunately, the principal of the school recently indicated that she was not interested in such a program. I was able to find email addresses of about half a dozen science teachers in Lawrence and all the principals of the middle schools. I sent them all emails and none responded. So then I got a contact of a friend who was a retired middle school teacher, science teacher from Lexington, and another one who was a retired middle school math teacher who became a principal in Belmont, to ask them, why aren't these people responding? Can they give me any advice? And I went through my presentation with them, and the kind of feedback that I received, they said to me, well, one of the things you have to do is you have to make the teachers feel like you're helping them do their job. And then they gave me, which was very helpful, they gave me a publication that was done in 2016 of the curriculum requirements in the STEM curriculum for middle school. So I went back, and all the demonstrations, I referenced points in the guidelines, and I still got no response. So that's Lawrence. It's interesting to see that in Lawrence, there are no listed after-school STEM programs, and they don't even boast about having STEM academies like they do, for instance, in Roxbury, or if you look at Lowell. So what I'm going to do is I'm going to show you what demonstrations I proposed, what props I was going to use. And before I start, which will be in a minute, I want you to realize that, as I said before, this is the middle school. It's not high school. They haven't yet had any algebra, and they suffered during the pandemic for basically missing 2 years of school. So no equations are included, which is quite a constraint. It's kind of densely worded intentionally so that I could leave copies of the presentation with teachers as reference. And I try to explain things through familiar experiences when possible, so that the students would recognize it and would have things they could talk to their parents about. For example, you'll see when we showed them light scattering, and we showed them that sunlight was composed of a lot of different wavelengths. Then we discussed, why is the sky blue, which is a classic question. So now I'm going to start the presentation. Does anybody have any questions now before I start?
Have to practice.
Excuse me?
The base.
I think we have a background conversation, Wayne, go ahead.
Okay, I'll just start then.
Or from Carol, or the other Carol.
Ron, could you mute all of us?
Yeah, that's good. Yeah. Okay.
Do you see my screen?
Not at
I
the
don't
moment.
see what, oh, here it
Oh,
comes.
there you go. Yeah.
Okay,
Now you can make it full screen, I think.
yes, that's what I just did, I think.
There you go. Perfect.
Okay, so this is what I'm doing. I started this a while ago, as you could see. Here's my contact information if anybody would like to participate or help. I certainly welcome the criticism or suggestions of people who have experience in this. And I told you some of the things that I've already tried and failed, which is like to get into schools in one particular town, city, which is Lawrence. Let me give you an idea. Here's what's published about the Lawrence public school performance. As I said, they have no after-school STEM programs, anything that I could find. This is probably based on the MCAS exams. Yes, it is. The state average is well, it went below 60%. You can see what it was. The state average is in the red. The Lawrence average is in the blue or green. These are the math test scores. So they were like 31% of, I don't know if this is percent of correct answers on the exam, but it doesn't matter as a relative measure. They were 31% and the average for the state was 51%. So they're doing pretty poorly, and reading was about the same. Now for these STEM academies, they're public schools, so they're required to show you what publicly put on the record what the performance of the school was. Now that's not required of these nonprofit after-school programs. They're on their own. They don't involve the public school system. So if you look at these bar graphs here, this is in a STEM academy. And look at, for example, at this school. So the light blue is this school, the STEM academy. The one in the middle is the district, which means Roxbury, which is a rather poor area. And the dark blue is the entire state. In math, for a STEM academy, they're very low. They're the light blue compared to even their district, which is somewhat puzzling, compared to even the schools in their area. And in reading, they're pretty poor. In science, they're a little bit better. They're still well below the state average. So it seems like going into a school like that might be promising. You might be able to, they might accept someone to come in and help out their students. Here's another so-called STEM academy in Lowell. And it's funny how they advertise. You know, they say they're preparing their students for STEM careers. I'm not sure how you do career preparation in middle school, but many of them boast that they're learning coding, which I also find a bit, I don't know how to say it, maybe disingenuous. I don't know what value it is, what coding they learn, coding skills they learn in middle school. And in any case, anybody who has a degree in science or engineering has had to do coding at some point. So what are they talking about? They're not making these people into computer scientists. They're just teaching them some kind of low-level coding. I know when my son worked at Amazon Web Services, he would say, well, the software engineers here are very highly paid. They're all computer scientists. They're not people who learned coding in middle school. So if you look at them, again, these are different bar graphs than the ones in the previous slide. So, but basically the two bars on the left are better than average. The more left it is, the better it is. They exceed expectations in the far left bar, and in the far right bar, they're well below expectations. Well, here's a STEM academy, our school here, and you could hardly see the exceeding expectations bar. And again, even in the district, it's better than the STEM academy. I don't understand that. So is the STEM academy achieving its goals? They're supposed to be teaching the kids science and math, and yet they do worse than the schools in the same district and much worse than the schools in this state. So there's something wrong there. You would think that they might be receptive to somebody coming in and helping out. That's the next thing that I would try, is to try and talk to these schools. I would still rather do an in-school program, again, because, well, these students, by the way, let me back up a second. This is not like the public high schools in New York, like that you may have heard of, like Bronx High School of Science, Stuyvesant High School, High School of Music and Art. Those all require you to pass entrance exams to get into them. These are open to anybody who applies. I think they have a lottery system for admission. This is what I got from one of the people who I spoke to, who I said was a friend of a friend, who was a retired middle school science teacher in Lexington. They gave me a copy of the Mass STEM Curriculum Guidelines. So before I discuss each demonstration that I'm proposing, I'll reference some things in the guidelines to show you that it should be relevant for the program. So the first, this is just an introduction. What I proposed to the guy when I was in Lawrence, again, I'm open to any suggestions. I said what I would do. I told him I wanted to do demonstrations in the classroom. He first said to me, well, could you do them in front of general, if we have an assembly of the whole school, and you do them at a full school assembly instead of going into the individual classrooms? And I said, no, because as much as possible, I prefer for them to be participatory. And I can't do that with a whole school assembly. I said, if you're going to do a whole school assembly, you might as well show them a video on a screen. I said, but at the whole school assembly, I'll introduce myself. And these are my notes to myself, what I was going to say to them. Tell them where I come from, where I got my passion for science, and then say, you know, one of the things, a few years ago, I gave a talk at kind of an adult education session at Middlesex Community College. And the title of my talk was Think Like a Scientist. And I noticed that the thing that they were most interested in was when I explained everyday experiences with science. And that's kind of this to get them interested in, you know, why is the sky blue? I asked them if they all have gardens, if they water the plants, how does the water get from the roots to the top of the plant? Told them, you know, there are giant sequoia trees in California that are over 200 feet tall. I asked them how big can bugs grow. They've seen monster movies which show bugs the size of elephants. And if you do a little bit of math, you could show that bugs will never get that big. And there's just some interesting things in here. You know, why do figure skaters spin faster when they pull their arms and legs in? Anybody who's taken freshman physics knows about angular momentum conservation. Things like this. I also think that, you know, if it were me, or I would hope some of the kids, that you tell them something like, look at how marvelous it is. We're seeing videos from Mars. They have a rover that's landed on Mars. Would you like to be one of the scientists or engineers who designs that equipment? Wouldn't that be exciting? It would take you about 335 years driving at highway speeds to drive to Mars. we're getting videos in real time from Mars. We have a James Webb telescope, which is going to tell us what happened over 13 billion years ago. To me, that's all amazing stuff. You know, maybe these kids haven't thought about it. The last thing I would ask them is raise your hand if you know a professional scientist or engineer, because that's what I'm concerned about. I don't know that these kids have role models. See how many raise their hands? And the last question is to show them that, you know, women can excel in science. Does anybody know who was the only person to win a Nobel Prize, both in physics and chemistry? And that was Marie Curie. Not to mention that in recent years, a lot of the Nobel Prizes in physics and chemistry have gone to women. These kind of things, we don't have to go through it. This was notes to myself when I do a particular demonstration, you know, what I want to cover, what kind of materials I'm going to need. So in the first demonstration, we were responding to something requirements in the curriculum guidelines, quoting them. One of the things they want to teach is developing and using models. Another is analyzing and interpreting data. And the third one is heat transfer. So we're going to cover some of those things. This is very simple. Again, it uses low-cost props, uses a hot plate, a beaker of water, and thermometers. And kids are going to come up and take turns and take measurements of the water temperature over time and plot it. I asked these middle school teachers whether they know how to plot a graph, and they told me that they do. And so I was going to ask them, what do you think the graph will look like before we plot it? I say we have a fixed volume of water. We turn the hot plate to a fixed temperature. So what do you think will happen if we measure the temperature rise after 5 minutes? We write it down, and then we measure the temperature rise in the next 5 minutes. And perhaps they'll say, well, it should be the same as in the first 5 minutes. You have the same volume of water, and you have the same temperature setting. So then what they'll describe is a constant slope. So they should expect to see a linear plot. But then there's a surprise when the water starts boiling. As you all know, the temperature becomes constant after that. And that leads into some issues of extrapolating data. So we were going to discuss, as it says, analyzing and interpreting data. This may seem like an advanced topic, but I was going to tell them what they're going to see is that they may expect a straight line, but they're going to see points like the one that's down here that go up, they're a bit scattered. All data will have random errors. There are unpredictable errors, which always occur when you do measurements. They don't have to understand. I'm not going to explain different types of noise like Johnson noise or things like that, but there's fundamental fluctuations associated with measurement devices. And it could be from random sources. It could be picking up signals from somewhere else. And then there's systematic errors, which are things that are always the same, but can be removed from your data by subtraction or division of each data point. Now, I showed this to my son, who's a college graduate in physics, and he said, they'll never understand that. So I said, well, yeah, I'm going to give them a simple example. Everybody's had an electronic scale at home, and you probably noticed when you stand on the scale, if you shift your weight, the reading changes. I was going to say that's a random error. If you jumped on and off the scale 10 times and recorded the number, and you weighed 75 pounds, maybe it would say 76, maybe it would say 74, maybe it would say 75. And suppose before you jumped on the scale, you noticed that as soon as you turned it on, it would read 1 pound, and you couldn't zero it. That's a systematic error. So you know when you get on and it reads 76, you really only weigh 75 because it reads 1 pound when there's nothing on the scale. And then I told them, typically when you have data, you don't just draw lines between all the points. You have a theoretical graph, and you draw a theoretical graph to fit the points and to minimize the total differences between the theory and the experimental points, without getting into, of course, linear least squares, fits, and things like that. That's basically the concept that you're using. So they'll understand that when they measure things, which I think a lot of people are disappointed at when they first measure something in a laboratory, that it doesn't exactly fit the theory. There's going to be random errors, and it could be systematic errors, which you can remove. And here's one. It's not reliable to extrapolate data. We all know about extrapolating data. That's mostly done by economists. And that involves an assumption that the plotted graph can be extended in the same shape as what you've already seen. Without a theory which predicts the observed shape, that could be problematic. You don't know, but for example, look at our own data. When they plot that, they're going to see that it's linear until they reach the boiling point, and then it's going to flatten out. The temperature is going to stay constant. If they thought their theory said that it should continue to increase linearly, they wouldn't know that it flattened out, and then the extrapolation would give the wrong answer. There's also, I mentioned what interpolation is. You don't have a theory. You don't draw a theoretical plot through the points. You could always interpolate using the discrete data points. If you want to find out what the value would be in between those 2 points, just take the average of the 2 points or whatever. Here's another one where you guys who do communication theory know about the term aliasing when you do digital sampling. But basically, if you take points and they're sparse and far apart, and you make an assumption because you don't have a theory about what that graph is going to look like, you could be way off. Suppose you had this sinusoidal oscillation of the real data, and you only took 3 points, and you said, aha, it forms a straight line. You'd be way off with the actual data. So this is telling them something about data analysis. There's no advanced math in this discussion, just concepts. My attitude is if they see these things over and over again, they sink in eventually. They see something about extrapolation, or they see something about random errors, they'll say, oh yeah, I've seen that before. And eventually they'll understand it. Then I would say to them, well, suppose your mom says, can you put some water on the stove and tell me when it's boiling? How do you know that it's boiling? You know, we just did this experiment where we measured the temperature, and when it reached the boiling point, temperature flattened out, didn't get any hotter. Well, then I start off by telling them, you know, in a sealed container with a lid on it, what is the vapor pressure? That's the pressure you would measure above the liquid, and that increases with increasing temperature. So we defined vapor pressure. I say, well, how do you know that it's boiling when you look at it? This is kind of teaching them about observation. And they'll probably say, we see big bubbles, lots of big bubbles coming up and bursting. And say, well, why do you see big bubbles? What do you have to do to inflate a balloon or to inflate a bicycle tire? Well, the pressure inside has to just exceed the pressure outside in order for it to expand. When you see those big bubbles expanding, that means that the steam pressure is greater than the atmospheric pressure, plus a little difference due to the weight of the water, but it doesn't matter. And then, you know, I don't know how many of them have parents who know anything about science, but sometimes I think if you give them little fun facts, maybe they'll go home and tell their parents, who'll be impressed that they know something. You go on the top of a tall mountain, the atmospheric pressure is going to be lower than it is at sea level. So the boiling temperature is going to be lower. So if you want to cook your boiled eggs, you're going to have to cook them longer. And to give you an example, on Mount Everest, which is the tallest peak, the boiling temperature is about 69 Celsius instead of 100 Celsius, which it is at atmospheric pressure. It's 157 Fahrenheit. Also, here's another thing they're familiar with. If you dissolve salt in the water, it lowers its vapor pressure so that it takes more heat to boil. And note that dissolving salt in water will also lower its freezing temperature. That's why people spread salt to prevent people from slipping on the ice outside. It makes the ice melt because it lowers the freezing temperature below the outside temperature, so it stays liquid. So here they learned about something about data. They learned something about boiling. They're supposed to learn about heat flow. So I threw that in there because you know you have the hot plate in contact with the beaker, and so we discuss a few things about heat flow. when two things are in contact, heat will always flow from the hotter one, higher temperature, to the cooler one at lower temperature, until the two temperatures become equal. The greater the temperature difference, the faster will be the heat flow. For example, your warm body will lose heat to the cold winter air. That's why you feel cold in the wintertime. And how do I move? I got to move these pictures out of the way. So I asked them a few questions. I say, when you put your hand above a stove, your hand feels warm. Why does your hand feel warm? Well, actually, a large part of the reason is radiative heating. Anything that's hot also radiates light. And in this case, as you see when you heat an electric stove, as it warms up, it turns orange. The color changes because the wavelength of the light that's emitted is changing. And if your hand absorbs some of that light, then your hand will get warmer. That's in fact how a microwave heats things. If you open the microwave oven, after you've cooked something in the microwave, the air doesn't feel warm, but the thing that you were heating was heated by absorbing microwaves. But also the air above the stove, immediately above the hot stove, will also be warmer, as you can see here, and you'll feel that with your hand. So then we ask a question, again, considering everyday experience, how do you cool yourself with a fan if it only moves the air in the room without cooling it like an air conditioner? Ask anybody, does anybody know? Well, the hint is in this graph. You see that the temperature is warmer right near the surface. You have a fan, blow away the hot air near the surface. And as we said, the greater the temperature difference, the faster the heat flow. So now your warm body is in contact with the cooler air. And so it cools off faster. And then try to get them to think about wind chill, which is kind of confusing when they tell you that on the weather report if you don't know anything about it. They'll say, well, today is 30 degrees, but it feels like it's 20 with the wind chill because it's 15-mile-per-hour winds or whatever they are. What does that mean? It means that it's 30 degrees, but you feel as if it's 20 degrees without a wind because it's 30 degrees with a wind. Why does the wind make a difference? Just like we discussed with the fan. The wind chill only has meaning for things that are generating heat. So what do you think? Can you measure it with a thermometer? The answer is, of course, no. You cannot measure wind chill with a thermometer. The thermometer only measures the air temperature. Now I talk about how surface area is used. Things with large surface area are used to remove heat. And here's a motorcycle engine. Hello? Here's a motorcycle engine, and it has fins on it. And these fins increase the surface area that's exposed to the cool air to enable it to remove heat. Notice that the fins on the engine on the cylinder are all horizontal. So that when the motorcycle moves to the right, which is moving forward, there's a wind going through the fins that way. If the fins were all vertical, they just block the flow of air. So that wind is just like a fan that cools you off. It cools the surface off. And we know that the fins increase surface area. You could easily see that. Because if I have something like this, which is 8 by 6 inches, but I don't know if you can see that, but it's got a fin on it. Single fin in this case. If I open it up, it's now 8 by 11 inches. That fin added a lot of extra area. If I had multiple fins, I would add that much more surface area to take away heat. And the last thing is some observations that they may have had, again, from their everyday life. Do any of you have pet hamsters? Have you ever noticed how they sleep? When they sleep, they huddle together. Why do they do that? Well, if you're a warm-blooded animal, then it takes fuel, oxygen, and food to keep your body warm. You don't want to lose your body heat. your body heat is lost through your skin, which is the outside. So an important factor is the ratio of the surface area of the skin to the volume inside, or the size, because the volume is where the heat is being created. The skin is where the heat is being lost. But since you have not had the math to be able to calculate volume and surface area, we'll do something a little bit simpler, and we'll be looking at, in 2 dimensions, at the perimeter as the outside and the area as the inside. So we'll be looking at the ratio of the perimeter to the inside area. So we take this small green square and we just count the perimeter, it's 8 units. If we count the squares in the inside, it's 4 units. So the ratio of the outside to the inside is 8 to 4. We look at the big red square, we count all the way around 1, 2, 3, 4, 5, 6, 7, 8. The perimeter is equal to 16, and the inside area is also 16 units. So you can see in the smaller one, there's more skin, there's more outside per inside. So small animals that are warm-blooded are going to lose a lot of their heat through their skin. In fact, I was watching a nature show on National Geographic the other day, and they talked about a shrew, which is about 2 inches long, smaller than a mouse. It's this ferocious little creature. It has to eat every 2 hours to maintain its body temperature. Another example of this is mittens versus gloves. If you're a skier, you know that mittens are much warmer than gloves. You wear gloves so you can manipulate things with your hands. But mittens keep your fingers together. Gloves separate them. In a way, you can think of the fingers in the glove as like the fins that we showed on the last slide. They're going to lose heat faster. So mittens would be warmer. Another funny thing, as a scientist, you think about all these different things. You say, why is that like that? Why do the hamsters all sleep together? Oh, by the way, backing up a bit, you could see that the little green square hamster, if he's sleeping next to these 3 other little red square hamsters, then he looks like the big red square hamster. So he doesn't lose as much heat. Hamsters can't buy coats on, Amazon. But another surface to volume, an interesting thing, is to look at bugs. If you see monster movies and you see giant bugs the size of elephants, they get scared and say, oh my gosh, can they be that big? I've never seen a bug that big. Well, in fact, they can't. They can't be because bugs don't have lungs. Your lungs are like pumps that pump the air in and out of your body. Bugs have to depend on little holes. They have to depend in their skin, and the air flows through the little holes through a process they call diffusion. But anyway, the air comes through the little holes, and as the bug gets bigger and bigger, remember, its volume increases in 3 dimensions, its surface area only increases in 2 dimensions. So as it gets bigger and bigger, it has a lot more volume for a smaller amount of surface area. It doesn't have enough surface area to get enough oxygen to feed that large volume. So hamsters might want to be bigger so that they can be more efficient and lose less heat. Bugs want to be smaller because they don't have lungs and they get all their oxygen through their skin. They need to have more skin, just like a little shrew is very small, has little inside and a lot of outside. So that's the end of that one. I had another one that I thought of, which was, remember I asked the question, when you water your plants, how does the water get to the top of the plant? This one's about osmotic pressure. In this crowd, most of you are engineers. I don't know, you might not think much about this kind of stuff, but one of the things that was recommended in the curriculum guidelines, let me see what I wrote here. I don't know how I'm doing in terms of time.
You're doing fine with time, Wayne. It's 11:24. We've got maybe another 15 minutes. I'd like to leave some time for Q&A, but you got
okay.
time.
Well, I'll go through this one fast. It shows that through osmotic pressure, This is to cover the area. It says develop and use a model to describe how parts of the cell contribute to cellular functions. So the cell membrane is a semi-permeable membrane, and so osmosis occurs. And here's an example of water and having enough osmotic pressure to create a column of water 265 feet tall. I would like to double check that because it sounds almost impossible, but I know that osmotic pressure in the formula, which I don't write down here, assumes an ideal solution, which means that the solute is dilute enough that the particles don't interact with each other. I would double check that, but in any case. And you can buy this osmosis kit. They can come and measure things, measure osmosis. This is a bigger description of it. This is $10. So I can buy that and I don't have to spend a large budget to do this kind of thing, and they can do measurements. The last one, which is probably more along the line of what I've been doing for the most of my career, is optical physics, fiber optic communication. And that fits, they actually have in the curriculum recommendation, it says waves and their application in technologies for information transfer. So this one would be a 2-day thing. Day one would be waves, frequency and wavelength. And day 2 would be optical fibers as light pipes. Okay. It says, I have a message here. I don't know what it is. Low system resources may affect your audio quality. Try closing some. Well, you're not having problems hearing me, are you? Okay, here are what waves, like electromagnetic waves. Light is an electromagnetic wave. You don't need to know what an electromagnetic wave means, except we're going to learn what frequency and wavelength mean. If you looked at these two waves and you stood on this side of them, first of all, if you sat on a peak and measured how fast you were traveling, that would tell you the wave velocity. If you looked at the wave from the side and you counted how many peaks pass per second, that will tell you the frequency. So if these two are traveling at the same velocity, then this one obviously has a higher frequency than that. The upper one will have more peaks passing in per second, which engineers call hertz. So 10 peaks per second is 10 hertz. Has nothing to do with renting cars. It has to do with a guy who was a radio engineer. You can also characterize these waves by their wavelength. If you took a still snapshot of the wave at any time and measured the distance between the peaks, then a longer wavelength corresponds to a lower frequency. You can characterize these waves by their wavelength or their frequency. It's kind of interesting because for electromagnetic waves, I don't have the picture of this picture blocking my view, but anyway. For electromagnetic waves, here's the electromagnetic spectrum. These are all the same thing. They're all electromagnetic waves, just of different wavelength. Radio frequency is the longest wavelength. If you listen on your radio dial to a signal and it says 100, that's 100 megahertz, 100 million hertz. And then your cell phone transmits a near microwave. The 1 gigahertz, which is kind of between radio and microwave, the wavelength is about that much. It's a centimeter. So 100 megahertz radio, the wavelength would be 10 centimeters, which is about 4 inches. And visible light is too small to see, but red light has a longer wavelength than blue light. And then you go to ultraviolet, which is a shorter wavelength, gamma rays. Again, if these peaks are higher, it means there's more energy in the field, in the electromagnetic field, and the light is brighter. But again, radio waves are the same as microwaves, are the same as infrared, same as visible. They're all electromagnetic waves. One interesting thing is the electromagnetic waves are generated in an antenna by accelerating motion of electrons up and down. Every time charged particles are accelerated, they radiate electromagnetic waves. But do you know that if you accelerate two masses, you will radiate gravitational waves? I mean, I know you might think I'm an attractive guy, but you don't feel my gravity. Gravity is a much weaker force than electromagnetic forces. But Einstein predicted over 100 years ago that there would be gravitational waves. And when they recently observed them with this wonderful experiment in about 2015, those guys won a Nobel Prize. And they saw two stars colliding, and it sent out these very weak waves, which basically cause ripples in space, like when you throw a pebble in a pond. And they were able to detect them. Now here's sound waves. Sound waves are another type of waves. They're just basically pressure waves caused by vibrations. You can see this tuning fork, and these dots are molecules of air. One important difference between sound waves and light waves is light waves can travel in a vacuum. What I mean by a vacuum is if you look on the right at the sound is a pressure wave, those little dots are molecules. The one in between where the wave is at the lowest is a vacuum, basically. A vacuum is when the pressure is very low. When you think of your vacuum cleaner, it has a fan in it, which blows the air out of the internal chamber and lowers the pressure. So the outside pressure is greater, pushes the stuff into the vacuum. A complete vacuum would be to have no dots there, nothing there. A sound wave needs a material to travel in. It can travel in gas in the air, it can travel in the water, in a liquid, or in a solid, but it can't travel in a vacuum. If you want to communicate satellite to satellite in outer space, you have to use light. You can't use sound. And by the way, the molecules aren't actually moving. When you see waves, only the disturbance is moving, the peaks. When you see water waves, the ocean isn't moving. It isn't moving from where it is. Just the waves are moving. Think of the spectators at a stadium doing the wave, where they all stand up, peaks, and then the next section stands up, and then the next section. None of them move out of their seats. We have a demonstration. One of the props we have for this is I've got a prism like this set up, and it's dispersing sunlight into the different colors. The red is the longest wavelength. The blue is a shorter wavelength or a higher frequency. And the reason it bends in the glass is that in the glass, the different frequencies travel at different speeds, and that causes it to bend. That's called dispersion. Remember that, because we'll come back to it later when we discuss why the sky is blue. Oh, actually, when we discuss communication as well. Here's a very interesting one about sound. All right, do any of you play a musical instrument? If you play a musical instrument, you know that the orchestra has to tune up. When you play a middle C, the piano has to tune to the same note as a trumpet or a violin, yet you can recognize right away that it's a piano playing or a trumpet playing or a guitar playing, and you could distinguish it from a violin, but they're all playing the same note. How can that be? Well, here's a sound wave from a flute. It looks a lot like the sound wave that we saw on the first slide, which was a single frequency sound wave, except it's a little pointier. But look at the distance between the peaks. They're the same as the distance between the peak in the second one, which is a piano playing the same note, but the very top of the peaks, the same distance apart. That defines the fundamental frequency. That's what you hear when you recognize a note. It's a middle C. And look at the trumpet. It's even more complicated, but the fundamental frequency, you can still see these peaks. Now, if you took a frequency spectrum, you had something that could measure all the frequencies in this wave, you would find out, here's a guitar, the fundamental frequency is always the biggest, and then there's a smaller contribution from what's called the second harmonic. If the fundamental frequency is 330 hertz, second harmonic is a multiple of that, it's 660, the third harmonic is 990, and you could see, especially in the third harmonic, that it's much larger in the guitar than it is in the piano. And that's what gives the instrument the timbre. It makes you recognize it as that instrument. Again, the note you're hearing is the fundamental frequency, but there's a lot of other frequencies. And engineers have a name for this kind of analysis. We call it Fourier analysis. Anybody who looks at waves, like electrical engineers especially, and physicists, they know about Fourier. He was a French mathematician. And this type of analysis is used in all voice recognition systems like Siri and Alexa, you use all the time. All right, now I have another prop, which is an optical fiber. See that optical fiber? It's a pretty big one. I put it in this black box that I constructed, and I have another prop, which is a laser pointer. And it's a very weak laser. And when they look in the black box where there's not a lot of background light, they can come up and form a line and shine light through here, and they could see the light going through the fiber, and they could tilt the laser and see it bounce off internally and see total internal reflection, which is what guides it. And if they tip it too far, it will escape when it's beyond the critical angle. And it's the same thing you get in a fiber, except that a fiber is about twice the thickness of a human hair. And when you bend the fiber too small a radius, you exceed the critical angle and it loses the light. It no longer guides the light. But you can see something, but something else that's important here. By the way, almost all long distance fiber optic communication is done in optical fibers because you can bend them anywhere you want, just like taking electricity in a wire or light in a pipe. It's not going to curve around unless you have it guided in something like a glass fiber. So why can you see the red beam in a lucite rod, but not in the air? So I'll have the kids stand in a line and take turns, and they can shine the light through the rod or above the rod, and they'll see when it's above, they can't see the red light. When it goes through the lucite rod, they can see the red light. Why is that? That's because there's stronger light scattering in the rod. And if there's, in order to see the beam, some of the light has to come to your eye. If it's in this, or only in the direction of the beam, none of the light is coming to your eye. But if some of the light is coming to your eye, that means some of it, if you're sending a signal through a fiber, that means some of it is escaping and the signal is getting weaker and weaker. So fibers in the fiber optic system, you need to have amplifiers because of that. And the reason, again, you could see it in this glass rod is because of scattering. So now that we know about scattering, we know about dispersion, wavelength, we could talk about why the sky is blue and red on the horizon when the sun sets. Well, this guy, Lord Rayleigh, did the theory, and he showed that shorter wavelengths scatter more strongly. Shorter wavelengths are blue, longer wavelengths are red. The sun is like a light bulb. It emits in all different directions. Most of the light that goes backwards and sideways, you wouldn't see unless it was scattered and its direction was changed. And the blue light is scattered much more than the red light. So you see the blue light. Red light, you would only see if it's coming straight toward you because it doesn't scatter as much. However, when the sun is setting or rising, it's on the horizon, it travels a longer distance through the atmosphere. So the blue light is scattered even more. That's scattered out of your point of view. And what you mostly see is the light that goes all the way through without much scattering. That's the red light. So you can see the blue light during the day because that's a light going in all different directions. The only way it can get to your eye is by scattering, and the blue light scatters a lot, the red light does not. In the evening when the sun rises, it's the opposite. You only see the light that's coming straight at you, travels a longer path, and so all the short wavelengths are scattered out. Go home and tell your parents about that, what you learned in school. And here I'm showing you a long distance fiber optic link. It's a little complicated. Here you have a pulse coming in. To transmit information, you have to turn something on and off. You have to change something. If I just transmit a constant tone at one frequency, like what you saw in the first slide, there's no information. I'm not telling you something. I could sing an extended note and keep, that's not talking, that's not telling you anything. You have to change something. In the old days, before they had telephones, they had Morse code. Here you can turn the light on and off. In Morse code, it was the same kind of thing. They had two possibilities. They had a dot, which was a short beep, and a dash, which was a long beep. And from that, they could spell out words. I could show you in the next slide how you could do that. But before we do that, you could see that in order to send all this information over a long distance, we send it through an optical fiber. and it's all digital, meaning it's all on-off signals, pulses on and off. There's a electric driver which drives a laser source, and the pulses are sent down the fiber. The fiber actually has amplifiers because there are scattering losses, and there's a photodetector. Photo means light, which converts the light into electricity, and an amplifier at the other end. Now, you might have some questions why each one of these lasers is being turned on and off at at about 10 billion times per second. They can send a lot more. The higher the frequency, the faster it's turned on and off, the more information they can transmit. And it's just like if you're going through a supermarket and there's only one checkout line and it takes 3 minutes for each person to go through, you're only going to get one person through every 3 minutes. You put 2 more checkout lines that are checking out at the same rate, you get 3 times, you get one person through every minute. So having more sources at different wavelengths can add, so you have a 10 billion times per second. Each one is turning on and off at 10 billion times per second. So why do you need so many? One of the things is all you guys with your ticky-tacky, TikTok and streaming video and all that. If you want to send video, it requires a lot. It has a lot more information content than if you're just sending voice or words or texting. You can imagine if you have any picture that you have is broken down into little pixels. Each pixel, you have to specify whether it's dark red, light red, green, red, blue, black, white. You have to specify all that for zillions of pixels. So when you send video, you require a lot more information rate than when you're just sending voice. And actually in today's systems, the number of channels there is limited by the amplifier. The amplifier has a certain range of wavelengths that it can amplify. And you could say, well, then why don't I just put more colors into that same range, put them closer together in wavelength? If they get too close together in wavelength, then when you try and separate them on the other side, you try and look at wavelength number 3, which engineers and scientists like to use a Greek letter lambda as a symbol for wavelength. Wavelength number 3, you try and separate that, and you can get the leakage from wavelength number 2 and wavelength number 4 if they're very close together. So that limits the number of channels you could put in. How about the rate of each one? Well, actually, some of the work that I and some of my colleagues did greatly increased the rate at which the lasers can turn on and off. But we still have to deal with the electronics, and it's much harder to get electronics. It's going way over 10 gigahertz frequencies. It gets very expensive, and there are other technical issues with it. But another one is the dispersion that you saw with the prism. You know that when you're traveling through a glass fiber, like the glass prism, the different frequencies will actually travel at different speeds. That's what allowed you to separate the different colors. Now, if you want to get to higher and higher data rates, you have to use shorter and shorter pulses. And later on, you become an engineer and you understand Fourier analysis, you will understand that a shorter pulse has a lot more frequencies in it than a longer pulse. So these short pulses, because they have a lot of frequencies, and the frequencies are each traveling at a slightly different speed as they travel a long distance, a narrow pulse is actually going to get wider. If you were on the highway and you were traveling at 65 miles per hour, and the car next to you in the next lane is traveling at 65 miles per hour, you'll stay right next to each other. If you speed up to 70 miles per hour, then an hour from now, you'll be 5 miles ahead of them. Well, that's what happens. Some frequencies get faster than the other ones lag behind, the pulse spreads out. And then you have something like this. You're expecting to have, in this picture, you have a 1 in the first time slot that you're detecting. You have a 0 in the second time slot. In this picture, you have a 0 in the first time slot and a 1 in the second one. So if you're sending a signal and starts out as a 1, it fills 1 time slot, and then it goes and spreads out, it's eventually going to get so wide, it'll leak into the second time slot. So the fat man can't fit in the bathtub anymore. And so you get errors because you're expecting to get a 0 here, and you get some confusion because this pulse has leaked over to the next time slot. That's called a dispersion penalty. That's because the different frequencies are traveling different speeds. That's about all I have to say on this. I could go on, but I don't know when you want to stop and have a
Yeah,
discussion.
this is actually, I'd like to, Wayne, I'd like to make sure we have a little bit of time for Q&A.
I
And
have some-
it's about quarter of. So we
Okay,
ought
let me
to
just say,
wrap
let
up
me
pretty
just
soon.
spend a few more minutes and I'll just quickly show you some of the other stuff. When do you
Okay.
want to be finished to discuss? Give me 5 minutes.
Yeah, 5 minutes. That's good.
So here's a high capacity fiber cable. See all the little fibers? This is like the thing that goes under the ocean, that lies on the ocean floor. In this picture, 3,456 fibers. Here, if you assume 10 channels, you can send about 1.5 million YouTube videos through each of those channels. You can send 50 billion videos at the same time. These kind of cables are strung under the ocean. They started stringing them in 1985. I have a map from 1998 of a whole bunch of transoceanic cables. Since then, companies like Facebook and Google are stringing their own cables because they don't have enough signal capacity. And the next one is just about manufacturing. I have another prop. It's a little laser module that I had from my time at Lasertron. And I'll explain to them all the, I won't go through it now, but all the considerations you have to do to make something like this. It's almost all material science, actually, Ron, you to appreciate that. It's all about solders and metallurgy, and here using Kovar because it has the same CTE as the glass, because each of these pins has to go through a glass bead that's pressed in there, so that because they're all containing different electrical signals, and there's a metal thing. And I go through all that, but it's interesting in here they do laser welding. Tell them here they have a control loop, just like your thermostat at home, and it controls the temperature of the laser, which is sitting on a thermoelectric cooler. But here there is actually a session in the guidelines that discusses manufacturing. I'll see what it says about it. Okay, I'm done. I hope I didn't speak too fast. Well, it's called section ETS2. It says materials, tools, and manufacturing. So they can get an idea of how much into engineering goes into it, just a little module like that, and all the materials knowledge that you have to have. Okay, I'm done. Hope that wasn't too fast. All right.
Great. Wayne, thank you. Thank you. I just want to say I think that the approach you've taken is very interesting, in that you have taken it upon yourself to look at curriculum guidelines, and then you've sort of related, particularly in the early early part of your presentation, you related some everyday experiences to those curriculum guidelines. And that strikes me as being a very effective way of doing something like what you're trying to do. I have to admit, as you got closer to the end, it got a little bit dense, a little bit thick. But I like what you have approached, the way you've approached this. And I do want to give our crew an opportunity to ask some questions, but I want to make one comment. You know, at the very beginning of your presentation, you made a comment about you know, the audience you're trying to reach, underprivileged children and so on. And, you know, that really touched a nerve in the following sense. I grew up in a town of about 150 people in the coal mines of Northeast Pennsylvania. There were 39 people in my graduating class from high school, which was a consolidation of about 10 different towns, each about the size of mine. And I had a teacher in that high school who taught chemistry, and he had the same sort of enthusiasm that you do. And he, you know, when I took my SATs, I got 400s in math and the verbal SATs, but I got a 750 in chemistry. And that got me into Penn State. It really did. If it hadn't been for the mentoring that this chemistry teacher directed towards me, I'm not sure that I would ever have gone to college. I probably would have been a coal miner. And I thank my lucky stars that he took enough interest in me to want to do that. So that really struck a chord. Very personal.
When I was in England at West Hartlepool, it was exactly the same. whenever I tell people who were British, who I met afterward, I said, oh, I lived a year in England as a child. They say, oh, where? And I go, West Hartlepool. They look at the ground. They go, why would you go there?
Yeah,
It's a
Yeah.
steel mill town. Hardly anybody there goes to university.
yeah, absolutely.
They
Absolutely.
all go to the mills.
Yep, we have some hands. Let's take some hands. Tom Hauper.
Yeah, I just wanted to share an experience I had in fourth grade. One of our students had a father who taught at Lehigh University in engineering, and he came and he had some dry ice with him. He had a big block of dry ice, and oh, I remember that. And his talking about how this went from a solid to a gas without going through the middle to a liquid. And he had our attention, and I just felt thrilled by what he was doing. And as I listened to you, I got to thinking that I think what makes a good scientist is not only the analytical skills he has, but his intuition, his being able to sense just without thinking that this should follow this and does it. And I would wish for a middle school science teacher or a number of them to sit in on your presentations and ask whether, I want to ask whether you work these minds a little too hard. If they are disadvantaged, I think your presentations might be great for some disadvantaged college freshmen. But that's just my own view. But I love what you're doing, and I wish you the best.
I've heard that, but I thought, I guess I naively thought that if I don't put any math in there, that they might be able to follow if I describe things like I described in 2 dimensions instead of I want to do surface area to volume. I know that they don't know how to calculate that. So I counted with a square and did the perimeter versus the area, which gives the same kind of, and tell them that as it gets larger, it's larger in 3 dimensions in the volume, but in the surface only gets larger in 2 dimensions. Anyway, I thought that maybe I would speak to them more slowly. I kind of rushed through this.
Yeah.
I mean, that's another thing.
We have a couple of hands up now. Albert and then John and then Mark have their hands up. So let's go to Albert. Now we have a little puppy in our house and he's doing something and I got to go check it out. Right back. But Albert, go ahead.
Wayne, I like very much what you're doing. I actually have a name for that, experiential learning, which even in college, I thought we should do more of what you presented. In the sense, for example, in college, you study stuff that may be too esoteric, that you cannot touch. Not all classes are like that, but many are. And experiential learning is very much better in my mind. Now, question, how is that school accepting what you're presenting? And I ask that because a good friend of mine who lived in Winchester and actually taught at MIT before retiring, offered to teach free of charge at the Winchester High School to teach math and physics. And to his surprise and mine, they turned him down, even though it was pro bono. He wasn't looking for any money. So how are you accepted by schools when you present your story here?
So the first time I presented it was to the assistant principal in Lawrence, who was very excited by it. And that was in August, and I didn't have it nearly as well developed. I just discussed some of the subjects. And he thought it'd be interesting, but we didn't go into any detail. As I said, I sent emails to a bunch of science teachers in Lawrence and a bunch of principals, and they didn't even respond. So they don't even know what I'm going to present. They do know what my background is. And I don't know if that's intimidating if you have a PhD, if they think that you're going to talk above the students' heads. I don't know what. When I spoke to the teachers from Lexington, they said, try and make it so that you're helping the teachers do their job. But that's why I included all the references to the curriculum guidelines. I thought that would make it more attractive, but I sent them this follow-up message with all those references and a description of what I was going to discuss. No response. So I think that the next step might be to try and go to a few of these STEM schools, not the nonprofit after-school STEM academy, but the STEM schools. Look at how poorly they're doing. They advertise that they're teaching these kids, I don't know what, coding, and their math scores are terrible.
Yeah. Let's go on. If we could, John, could we go to you? We're at 9:55, so we need to watch our time.
Rodney, I
Right.
just add that intimidation is what we thought was happening in Winchester High School. Where
Yeah, I think so
my
too.
buddy, so that's a big issue that has to be addressed to be successful.
Did you say intimidation?
Yeah.
Yeah,
Intimidation by the teachers.
Yes.
or
I'm
intimidation
afraid that
of the
someone
teacher.
will tell them they're not teaching it.
Mark has a comment that I know is relevant. So Mark, go ahead. We'll take John next after.
Yeah, one of the big things that, having spent in the second career 15 years at the McCall Middle School, working with special ed kids, if I had to make an approach to a middle school, you have to understand what the psychological ethos is in a middle school. Sixth grade, they're coming out of elementary school. It's a whole new experience. They're just getting used to people. The teachers are getting used to them. Seventh grade, whenever we had any project that we had to do to inculcate some special, learning principle, we do it seventh grade only. We always aim at the seventh graders. The eighth graders, they're on their way out there. They're cock of a walk now. They've been there 3 years. They know what's going on, and they're just worried about going on. And if you have to do it with the seventh graders and science, you've got to have some sort of incentive. I mean, if I were doing it, I would go to I would set up some sort of a competition with the seventh grade science teachers. They've had a year experience to know what kids might have some proclivities towards science. And you sort of set up a competition among them and say, we're going to have this special presentation and only certain students are going to qualify for it, and make it a contest type of thing. And that will appear to the middle school mentality. You're going into a class and going, I mean, the end of your presentation, to be honest, you talk about hurts, my hair hurt with all the stuff you threw out. And you've got about
I'm sorry.
a
What was the last thing
year
you
and a
said?
half, a year and a half of science. And most of that stuff you talked about really is in the first year, sixth grade science. And you set up a competition, make it something unusual, something that they gain, and the combination of the teachers identifying them and only picking certain ones. I think you can probably reach people who might be inclined to be involved in chemistry. But if that's the only way to me in the middle school atmosphere, that's going to happen.
Thanks for all your comments. And anybody who's willing to talk to me more and has advice, I left my phone number and email on the first slide. I can give it to Ron or anybody.
Yeah,
But,
yeah.
They wouldn't. I couldn't even get them to send me. I said, please tell me, respond, so at least I know that you read it. And no response. And I said, we can have a brief phone call. No commitment at all. If you don't like what I'm doing, say you're not interested. But let me explain it to you.
Well, I mean, I had over the years, I've been offering a program at MIT. It's still being offered. It started in 1989. It's called the Science and Engineering Program for Teachers. And one thing that I might propose, Wayne, is that I forward this video, our recording, onto this community. There are over 1,200. I don't know how many, probably 2,000 teachers involved at this point. And there may be, what we need to do is to find someone who's willing to engage and start a ball rolling. Because I think what you're trying to do has real merit, but it's not a trivial exercise. That's for sure. Let's go on to John. I think John had his hand up. John?
Yeah, I really don't have a whole lot to add after all this other discussion, but I was thinking another way it's in might be not through the school, but through the Boys and Girls Club. I think like in a place like Lawrence, there's a lot of after school activities at Boys and Girls Club where they play basketball and things like that. It might be that you could set up a program where you have sessions where you do science demonstrations. Anyway, that might be one way in. And Hugh has his hand up.
Oh, okay.
Might sound
But he
like a
has
good
his, he's
suggestion.
muted.
I don't see any other hands. Do I? Anyone have their hand?
There's
Oh, I'm
Hugh.
sorry. Yeah, Arthur. Oh, I'm sorry. Go ahead.
Hi,
You're
I'm sorry
muted,
about my,
Arthur.
this is Hugh Wright. I'm sorry about my video. It's on the Fritz today. I taught a little bit of seventh grade after school in Winchester. And what I found, some of the challenges, first of all, I'd like to sign up for your course. I think it was good. Some of the challenges is it's very important to avoid despair, because I learned afterwards that some of the students that took my course felt like, oh my God, this is more than I'm capable of. So it was counterproductive. I got some teacher assistants, aides. They're actually parents of some of the kids that were in the class. That was very helpful. Anyway, I have some comments that I don't think everybody wants to hear, and I'll share with you on email. Thanks.
Thank you.
Thanks.
Please
Thank you
do.
very much. Thank you. Now, Arthur, yes, you have to unmute, Arthur. Hold on.
Are you
There you
okay?
go. Yeah. You have the final comment where we're about noon.
Yeah, I saw the examples for the earlier examples, such as heat transfer and so on, were really very appropriate. But I'm just wondering, as you got into the optics area and communications, which I happen to be very familiar with, and I could more or less follow, how much success you can have with kids of that level, and how much time do you have to present these examples in?
Well, I'm hoping that, even something as stupid simple as this, this optical fiber. I mean, they could see things. You could see the red light bouncing around inside. I think demonstrations like that I hope are helpful. I didn't, like I said, I didn't use any math. I thought of saying, they say something in the guidelines. It's very strange that they should learn you could transmit information with on-off pulses. But I didn't know. I was almost going to do something where I said, look how many combinations you can get. You have these, let's say you have a time slot and you can get a 1 or a 0. Then you have another time slot, you can get another 1 or a 0. Each time you have another time slot, you're multiplying the number of possible combinations by 2. They can do multiplication. They could see where it's going and say 5 time slots is 2 to the 5th. I won't say 2 to the 5th. That's 32 possibilities. And say that's more than the letters of the alphabet. If you wanted to do that and spell out the letters of the alphabet, you could do that. It's a little harder to, and I'm not a communications engineer, to describe, how they do digital sound, how they send video and things like that. I can't describe the details of that. But I think it's good for them to learn to see for a first time, even like basic probability, how to think. When my son was in school in Lexington, in elementary school, the teacher had been a special needs teacher, but they gave different homework to different kids. I remember one day he had a homework assignment, which was basically to do all these probability calculations. Yeah. And I was surprised. I mean, I could show him how to do it, and you could show them other things, like you say, okay, you have 5 time slots, you have 32 possibilities. Suppose the second time slot was always going to be the same as the first. We call that correlation. Now you only have 16 possibilities. They don't have to know calculus. They have to, if they see something one time, then the next time they see it, they'll say, oh yeah, I didn't remember that, but some guy was talking about that before. And after they see it, and that's my philosophy. Yeah, I can try and go slowly to see that some kids are catching on. For me, what?
I think, Wayne, I think by associating familiar experiences, from music to wind chill to engines to cooling fins to animals, all of those things are familiar to the kinds of kids which you're interested in reaching. And I think by associating the science and technology behind, for example, a musical instrument, I think that's the kind of thing that might just engage kids. So I gotta say, I applaud what you're doing. I hope that maybe some of the folks online or in our program this morning will be willing to help in whatever way we can. But I will get back in touch with you in terms of this teachers crew that I have been working with for the
Well,
last
hope
week.
you sell it.
Yeah,
How do I get in? Because again, this isn't an after-school program is much easier because
Yeah.
you can do whatever you want. You're a
Yeah.
nonprofit group.
yeah,
These teachers have to follow these guidelines.
yeah.
And I don't know. I was shocked that they didn't respond. I think it's, I don't want to, I don't mean to sound arrogant, but I think it's maybe because I'm threatening, like you say. They don't want anybody to see. There's these general guidelines, but they don't say what you have to do day by day. I bet
Yeah.
there's a huge variation from among different teachers. on
No,
how
it's
well
a
they
challenge.
teach.
There's no doubt. And it takes patience and determination. But I think I see that in you. I know that you are intending to do something very useful for kids, and I'd like to see if I can help make it happen. Meanwhile, we ought to bring this to an end. It's getting close to the 12,
Okay,
after 12, and I just
Hope
want
I
you to
go
see this
too
guy.
fast.
This is Finn. He's a 10-week-old Cairn Terrier, and the noise I heard in my kitchen while we were online was my shoe. He got a hold of it, he started
okay,
chewing
well, I'm
and
glad it
banging
didn't
it
like
on the floor, so I had to rescue it. But I want to thank you all for joining us. And Wayne, thank
Thanks
you
for
again.
coming. And as I said, anybody who wants to contact me, I appreciate any advice.
Yeah.
I have another Zoom meeting with one of the few Lexington Middle School science teachers who responded to me. I think she responded because she was the teacher of my daughter, who's now 32 years old. And I'm going to have a Zoom meeting with her tomorrow afternoon. But again, Lexington isn't quite the same as, like I said, in Lexington,
Yeah.
it's a very highly educated community. That's why the school system is good. I guarantee it's the parents. You know that you will make sure your kids did well in school. Anybody who's an MIT and Harvard professor, don't you think they care whether their kids do well in school?
Yeah, you're right.
Yeah, but
All right,
teachers are in unions.
I'm sorry,
School
Bob.
teachers, my father was
I
in the
say
teachers union.
Part of his problem may be that teachers are in unions.
Well,
Yeah.
that may be an issue, but
But how
a
is
lot
that?
does
Well, anyway.
A lot of it's not the unions. What you have now, the teachers, they have to submit lesson plans ahead of time now. The orderly things, they're being channeled to do all these things on every day on a day-to-day basis. And there's very little freewheeling of science now. And as a result, when someone from the outside and everything you have to say is worthy, Warren, it's great stuff, Wayne. But I'm just saying, for them to interrupt these things they are now forced into adhering to because of school curriculum regulations, it just upsets. So it's tough.
Yeah, that's what I figured, but I'm trying to follow the curriculum guidelines anyway.
yeah.
I'm
Look,
not-
I mean, as I said, this is not an easy thing to do, but I think it's
No.
important to try to do something constructive here. And
do people here agree that middle school is the place to address these handicaps? I call them handicaps because these kids are at a real disadvantage. I mean, they don't have any mentors. They probably never met a professional scientist or engineer.
Yeah.
Half of them, most of them. Anyway.
Well, by the way, getting back to my idea of the Boys and Girls Clubs, I mean, I think that's a place where there's more leeway to create a new program as opposed to, as Mark was saying, in the high school, they got this day you're doing this, on this day you're doing that. And,
You might
they
be
got it
right.
figured out and they don't have time to try to deal with, how they would change it. They got a lot of other problems they're dealing with. So, but I think a place like the Boys and Girls Club, you could say, I'm going to offer you a new program,
But I'll tell you one thing, just to add a comment, and then we really should bring this to a close. I promised everyone that we always end at noon. With this teachers group that we've had teachers on our campus since 1989 in the summer. They come for a week, they spend a week with us, but they're in constant communication electronically. They've even set up their own server at MIT. And there's absolutely no doubt they have crowded curriculum. But what we're trying to do is to help them to shape some of the things they do. We're not trying to replace their chemistry or physics or math. We're trying to help them by introducing things that, like, I think what Wayne is doing, trying to introduce connectivity between life experiences and science and engineering. And it can work, but it takes some real effort. I've found that the MIT faculty have been very willing to engage with teachers, and they communicate on a regular basis. It's not that they come to campus and that's the end of the story. There is a line of communication that operates continuously. And I think what Wayne is doing is adding another dimension. And I just think it's important. Without the sort of educational experiences that I've had, I probably wouldn't have gone to college. I really wouldn't. And if there are kids who can benefit in the same way, and Wayne, what you're trying to do may engage some of those people, I think that's constructive. So I'm all for it. We'll have to talk about this again later, though.
For me, it would be very rewarding to have one or two kids walk up to me at the end of a demonstration and say,
yeah,
I'd like to talk to you more because I want to know how I could become a scientist or something.
Well, you know what? We can meet as we have in the past at my favorite office away from home, and that's Patisserie, or one of the other places in town. How's that?
Sure.
Okay, deal. All right, everyone. Take care. Have a good weekend, and thank you all for the
Thanks for
conversation.
and your suggestions are welcome.
Yes,
Thank you for caring.
okay.
Thank you, Wayne.
Thank you. Thanks, everybody. Take care.
Bye.